Welcome, everybody. Good afternoon. In this session about the atmosphere and its dynamic, with subtitle Infrasound Wave Propagation and Attenuation, Transport of Radionuclides, Global Circulation, Volcanoes, Climatology, Meteorology, and Noise Sources. My name is Robin Schoemaker. I work for the CTBTO in the International Data Center. I'm co-convener, together by my other co-convener, Ms. Daniela Gica, Head of National Data Center Romania. We both welcome you all here, the audience and especially the speakers, because they share their knowledge here, which is very important. And well, let's start. We're already late. I hope all the speakers are ready. And
the first speaker is Tereza. Sindelarova. Sorry, Tereza, but I try. So with infrasound observation at the station, PVCI, between 2019-2022, and the identification of the sources.
Okay, thank you. Good afternoon. I am Tereza Sindelarova, and I am an observer at the Czech microbarograph station PVCI, and I would like to introduce the array and our observations. So we will start with a short visit to the observatory. Then we will have a look at the infrasound observations and their seasonal variability and possible signal sources. These 4 DIVA plots are summaries of back-azimuths observed at PVCI in years 2019 to 2022. So this is the observatory Panská Ves, and the 3 array elements are highlighted in the picture. PVCI is a small array. Its aperture is just 200 meters, and it operates in the range from 0.05 to 4 Hertz. We process our infrasound data using PMCC software, and the seasonal summaries and statistics are obtained with DIVA. Our present study is based on measurements of a single station only, so we were not able to perform a localization procedure when searching for infrasound sources. Therefore, we based on the literature review, and then we were searching maps in the required back-azimuth. So these are the summer observations. Summer 2022 is shown as an example. The upper plot is a 2D histogram, frequency versus back-azimuth, and the color scale are apparent velocities or trace velocities. This plot includes only signals of duration longer than 30 seconds. Now let's have a closer look at the arrivals from the southwest. We can see that the frequency is around 0.2 Hertz, and that the signals arrive with quite high apparent velocities of up to 0.6 kilometers per second. According to the model by Lonzaka, who studied the relation between signal trace velocity and signal celerity, we assume that these detections could be microbaromes propagating in the thermospheric waveguide. Then the lower plot is a 1D histogram. Back-azimuths are on the horizontal axis. This plot summarizes detections at frequencies higher than 0.7 Hertz. We borrowed this threshold from the European Infrasound bulletin by Christoph Pilger et al. And it writes in the bulletin that signals of such high frequencies are expected to be mainly of anthropogenic origin. As for possible sources in the significant back-azimuth, the dominant peak at 90 degrees are signals from the war in Ukraine. These detections were verified with the bulletin of the International Seismological Center. Then at 150 degrees from the observatory, there are big refineries in Austria, Hungary, and Slovakia. And to the northwest or west from PVCI, there is an industrial region, Northwest Bohemia, with a small refinery and several brown coal mines. This source is about 60 to 80 kilometers distant from the observatory. It means it is somewhere around the inner margin of the geometrical shadow zone, and we expect that the visibility of this source is not influenced by the seasonality of the stratospheric waveguide. So these are the same plots, but for winter 2022. Here, please be not confused with the dates in the titles of the figures. Indeed, only winter detections are included. In winter, PVCI detects only arrivals from the northwest or from west. So it might seem easy to identify a source. We could point at microbaromes. But the frequency content of the detections extends up to 2 Hz, and moreover, a significant number of detections is in the range between 0.5 to 0.8 Hz, which is slightly above the microbaron band. So when considering winter sources for PVCI, we should certainly take into account this industrial region in Northwest Bohemia. There is also a big chemical industrial complex and a refinery in Leuna in Germany, which is at the back azimuth of 295 degrees from PVCI and at a distance of about 200 kilometers. But still, unexplained sources remain, particularly at the direction between 310 to 330 degrees. There was an idea whether our observations could be influenced by the big wind farms in the Western Europe or in the North Sea, but after a detailed review of literature, I guess this was not the best idea of my life, so I apologize for the misleading information in my abstract. This map is an overview of regional sources possibly detected at PVCI. It doesn't work, sorry. The observatory is shown as the black and white circle, and the directional rosette in the background are back azimuths detected in year 2022. This map is for local sources. Again, the observatory is highlighted with the black-white circle. And there are several small quarries just some 5-6 kilometers from PVCI. To the west from the observatory, there is the mentioned industrial region, Northwest Bohemia. And to the northeast, at a distance of 50 kilometers, there is the big brown coal mine and thermal power plant Turów. This source was already identified in the European Infrasound bulletin, and PVCI, however, it is quite close. PVCI does not detect this source regularly. We assume that the visibility of this source can be influenced by the shadow zone. So, the Czech microbarograph network is a member of Central and Eastern European Infrasound network. The CIN group focuses on identification and monitoring of infrasound sources in Central and Eastern Europe. And our group regularly issues Central and Eastern European bulletin, which can be downloaded at the CIN web portal. So this is the last slide. PVCI mainly detects arrivals from the northwest all year round. In winter, we get northwest arrivals only, so we assume there is likely no permanent local source to the east from the observatory. In summer, the back azimuths are more variable. They include arrivals from the west as well from the east. As possible signal sources were identified microbaromes, refineries and other industry, and mining activities. And from year 2022, we get a lot of detections from the war in Ukraine. I didn't focus on transient sources today, but they are regularly detected at PVCI. Among them, particularly North Sea sonic booms, again seasonic booms, and signals from convective storms. These signals include signals from lightning as well as from the mechanical motion of the weather systems. So that's all. Thank you.
So, questions for Tereza? Yes, Läslo, please.
Thank you. I'm not sure I fully got it, but you were talking about these sources around 300 degrees.
Yes.
And said, well, it might be windmills. But aren't the sonic booms on the North Sea enough to explain your observations?
Yes, they are there, but there are many signals of long durations which can't be explained by sonic booms. The duration of the signal is over 30 seconds, so I expect some permanent or long-lasting source there.
Okay, clear. Thanks.
I have a question. Do you observe sonic booms in local distance and let's say regional distance?
No, I haven't registered such a local sonic boom. I just know about these North Sea sonic booms and again seasonic booms. And as for local signals from aircraft, we can see the traffic above the observatory, but these are the rainbow signs from the moving plane, not the booms.
The local, no.
No.
Okay, thank you.
Thank you for your presentation. As a non-expert, I have the following question. Do you use the data for other purposes apart from treaty verification?
Come again, please.
Yeah. Do you use the infrasound data for other purposes apart than treaty verification?
We use the data rather for research purposes. We are not in the IMS.
Okay. Okay, thank you.
I think he means if you use the data from IDC, but
No.
Tereza is not an authorized user, so she has no access to the IMS data yet. She's trying to change this.
Okay, thank you.
Thank you.
Okay, so no question. Thank you. Thank you, Tereza.
We come to the next speaker, which is from Mr. Andry Harifidy Ramanantsoa from Madagascar, the Institute and Observatory of Geophysics and of Antananarivo. This is an online presentation, and I will check with the technicians if he is queued by now.
Going to present my work entitled Relation between Infrasound and Rainfall. Climate is regulated in general by ocean circulation, altitude, vegetation cover, distance land sea, and general circulation. Indian Ocean dipole, El Niño, Mozambique Channel trough regulate the rainfall in Madagascar as related by Malala et al. In 2018. In daily life, there are endogenous knowledge relating the rainfall in Madagascar. Some insects flying westward before rain, or birds sing, announcing the rainy season. According to these two different knowledges, we wonder why not we can use infrasound measurement during dry season to estimate the coming rainfall. The study is based on first observation and first approximation. Infrasound station I33MG is using microbarometer MB 2000 is used for data measurement. Data processing is done by DTK PMCC. Low frequency detections from 2003 to 2023 are used because infrasound low frequency is mainly produced by natural sources. Precipitation data used are from 2004 to 2022, and the data are retrieved from ECMWF ERA 5. Number of detection and the mean frequency are the parameters we used for this study. In general, there are two seasons in Madagascar, the rainy season from November in previous year to April, and the dry season from May to October. The period of sampling of infrasound measurement is from week 15, mid-April, to week 44, early November, for each year. In order to have all the data corresponding to dry season, we took the end of the previous rainy season and the beginning of the next rainy season. The dry season begins from week 19 to week 4. Precipitation data are used to know if precipitation is during the year is normal above 1000 millimeter, or precipitation during the year is low, less than 1000 millimeter. As example, the lowest precipitation is in 2017, and the highest precipitation is 2007. Infrasound detection numbers are categorized according to normal precipitation and low precipitation. Data average is shown in red for normal precipitation and in black for low precipitation. Frequencies are classified as well according to normal precipitation and low precipitation. Averages are marked in red for normal precipitation and in black for low precipitation. When we look at the plot without averages, we can't retrieve anything. And by calculating averages, we can make interpretation, and the interpretation is made from May to October. For the detection number, averages are quite similar. We cannot tell the difference. In terms of frequency, there is difference between infrasound measurements before normal precipitation and the measurement before low precipitation. Frequencies measured before normal precipitation are slightly higher, around 0.34 Hertz, than those before low precipitation, around 0.32 Hertz. We can say at first approximation that measured frequencies can estimate the rainfall for the next rainy season. We cannot draw a law to estimate rainfall because we have only 20 years of data. For the frequency, standard deviations vary from 0.25 to 0.32 for normal precipitation, and from 0.22 to 0.26 for low precipitation. To conclude, climate observation by means of infrasound is possible. For the first observation, we had good results. The relationship between infrasound and rainfall is obvious. And finally, further study needs to be undertaken to know which type of low-frequency infrasound can describe the most the rainfall. Is it the microbaromes or MAO? Thank you for your attention.
We thank Mr. Ramanantsoa for this pre-recorded presentation. So we go now to the next speaker.
The next speaker is Läslo with a long-term IMS infrasound measurement as a passive probe for climate change. Yes.
We have some time.
I have a bit of a hard time with my voice.
Yeah. If you want more, just let us know.
Okay, thank you, and thank you for giving me the opportunity to speak here. I'm going to discuss the IMS. Previous occasions we have spoken about glaciers in Greenland, where we saw climate signals in the melting and the calving of the glaciers. We published that work in GRL. There are new papers coming from that. But we extended our climate work into looking at acoustic travel times in the atmosphere. And I want to draw your attention to the graph on the right. I made that yesterday afternoon, and as you can see, I'm not much of a good drawer, but let me guide you through it. You'll see on top you see a winter situation in Europe with a snowy Mount Etna erupting and an observer in the Netherlands. The distance between Mount Etna and the Netherlands is about 1,800 kilometers. The Etna erupts at 1 o'clock, and the recording made by that person and a microphone in his hand, a woolen cap because it's winter, at 2:30. So that's 90 minutes travel time, and that you can see in the little mathematical thing I did there. So you see 1,800 kilometers divided by 90 times 60. 90 minutes times 60 seconds, that's 0.33 kilometers per second. And then we know that the atmosphere was -2 degrees. We repeat that experiment in summer, no snow on Etna. The guy switched from a woolen to a baseball cap. And the sound appears somewhat earlier, 2 minutes earlier. So now it travels at 0.34 kilometers per second, and it's 14 degrees Celsius in the atmosphere. This is, of course, a very simple thing, but it is the thing we are actually applying in atmospheric acoustics. In ocean acoustics, we have done it and seen the deep ocean warming due to climate change on the excellent hydrophone network of the IMS. Propagation is, of course, far more complex than shown here, but I wanted to show you this example because this is the simplicity sometimes of the work we are doing. There is some text to the left. Let's go through that. The IMS is an excellent global geophysical network. I think that's very important to mention because we have a network which we all want to keep, which we want to sustain, which we want to enhance even maybe, but it is already a network very well capable of its verification task. We know we continuously record hydroacoustic and infrasonic waves from a variety of sources and also ambient noise. The little drawing on the right is, of course, a deterministic source. It's a volcano, we know, that explodes and it leaves a pulse in the atmosphere. But you can do actually the same with ambient noise. You can do the same without knowing where the source is, without knowing the time that the source went off. That's called ambient noise interferometry. It's exactly the same setup, only that you don't know what the source is and you don't know the eruption or the explosion time or whatever. Might be a topic for another presentation. The propagation velocity, as shown, depends on temperature. So in the ocean, I should remember, T to the power of 3, Mark Pryor, power of 4, something like that. Atmosphere, square root of T. So there is a strong dependence of the propagation velocity on temperature. So measuring velocity or measuring travel time directly gives you a measure of temperature. Doing that over tens of years, of course, gives you an idea over the changes in the medium. So I hope I'm going to convince you that long-term infrasound measurements can serve as an independent proxy for climate change. My presentation time-wise is supposed to start now. Is it actually start? Yes. Yeah? So I can take a lot of extra time. This is what we have, the setup. So we are with a station here in the Russian Federation, an infrasound station, I-46 RU, a co-located seismic array, Zalavozo, ZALV, started operating in, or the first events reported in the REB in 2007, March of 2007, up to now. So you see the location on the left, you see the array layout. I only put a central element of the seismic array. And then the 4 infrasound sensors, large aperture array of over 2,000 meters in aperture. Then you see a map with a terrible amount of dots. So in the middle somewhere is the station. It's a seismoacoustic station, measures both seismic and acoustics. And then you see a lot of red dots. Well, to be precise, the number of dots is there written. Almost 15,000 dots, 15,000 seismoacoustic events in the REB. These are all open pit mines. Blasts in open pit mines. So you see the clusters of red dots. If you would have a Google Maps next to it, you would see open pit mines in the Russian Federation. Kazakhstan, big, deep open pit mines. Not even the moderate of explosion, I would say, because local magnitudes up to 4.3. That's a big explosion. Those are big explosions. Some seismic only events, so the red ones are all seismoacoustic events, both a seismic and an acoustic signal. The blue dots are earthquakes, so they are non-surface events, deep, so only seismic signals in the Altai Mountains. So a bulletin flushed with seismoacoustic events. Excuse me. Another drawing, the last one I promise. So we have a source and a receiver. Then we have the waves traveling to the solid earth. Somebody is nicely helping me with pointing, thank you. So we have the waves through the solid earth, the seismic waves. These waves are used for localization of the events in the REB. So the acoustic signals are not used for localization or for timing. Multiple arrays are actually used in the region to localize the sources and get the origin time. So that's our ground truth. It's of course not ground truth 0 or whatever, but that's, we have a location and we have an origin time. That's important for this analysis. Then we have the acoustic waves traveling through the atmosphere, of course, multiple paths. The seismic waves also do multiple paths, of course. But for this analysis, we are going to look at the atmosphere. So what do we assume? We assume that over this period, starting in 2007 up to now, that the solid earth is unchanged. So all changes we measure in travel time, in acoustic travel time, are due to changes in the medium, the atmosphere, as the solid earth is unchanged. Which is, I think, a decent assumption, but if anyone wants to challenge that, let's discuss it. So let me look at the text. We have that changes, yeah. So changes, that's important. Everything we are going to measure are changes in the atmosphere. So there we go. And then it's all about the lower frame. Don't worry too much about the top two frames. What I've done here is actually quite simple. I take the epicentral distance or horizontal distance or whatever you want to call it, the source receiver distance along the Earth's surface, and divide that by the acoustic travel time, which is the arrival time at the station minus the origin time. And the origin time we know from seismics and the distance we know from seismics. Then you get all the gray dots in the lower frame, and it says celerity on the axis. That's just a horizontal velocity for seismologists. Something around the sound speed, something like 300 meters a second. Well, the first thing, it is not getting better. The first thing, but that might also be because I'm much attracted by these kind of figures. I think that the structure in the gray dots is beautiful. because there is a yearly recurring structure of reverse smileys, I would say. So that might be somewhat harder for you to point out. But you see these reverse smileys. Well, they are because of the temperature increase in the atmosphere in summer. So in summertime, things are going a bit faster than in wintertime. So you get the reverse smiley. Then another thing that stands out are the vertical lines in winter. So there are enormous high velocities, up to 350 meters a second in winter. These are these sharp vertical lines. These are due to what's called sudden stratospheric warmings. In winter, the temperature in the stratosphere between, let's say, 20 and 50 kilometers altitude can increase by tens of degrees only in a few days. This is a sudden stratospheric warming. So you get a temperature increase in a few days of 20, 30, 40 degrees Celsius, which of course has an enormous influence on the travel time, as you can see here. Number is dramatic, the 20, 30, 40 degrees Celsius temperature increase, but don't forget that there is not so much mass up there, so heating it is a bit easier than heating the lower atmosphere. So a remarkable structure, recurring structure, in these about 15,000 gray dots. And then I fitted a line, a regression line through it, in blue and in red. In blue over the whole period, but you can see that in the first 2-3 years there weren't many, I should say, events. But if I fit that line over the whole period, I get a positive trend of 0.77 meters per second per year. So there is an increase in the propagation velocity of the acoustic waves in the atmosphere by about a meter per second per year from this analysis. A few data the first 3 years, so I also looked at the period of 2010 to 2022, and there you see similar number, 0.75. What's important in these kind of analysis, of course, is that the error is much smaller, an order of a magnitude smaller than the value itself. So it's 0.08 is the error versus 0.8 as an absolute value. I need to start rushing. Most terrible thing you can do in a presentation is showing a table. So here is your table. But I don't have really another way of doing this right, so I'm going to make it easy for you. You only need to focus on the right column. That's for the period 2010-2022. Why did I make this table? Well, you can pretty soon make an argument against the positive trend I found and say, well, something might have changed with the source distribution. You don't have a nice homogeneous source distribution, and the source distribution has changed over time, and that's causing the change in the velocities. That's a good argument. So what this table does, and only focus on the right column, it analyzes different back-azimuth segments and various distances. And the message here is, whatever you vary in distance or in back-azimuth, so in the source distribution, you always find a positive trend in the velocity over the years. It differs because my voice is getting it differs. Because if I only take the sources nearby, between 80 and 180 kilometers, the first bounce range for stratospheric or infrasound guys in the room, you see a higher value than when I go to larger distances. So from 180 to 900 kilometers, the values are typically about half the value of for nearby sources. So we go up to 2 meters per second per year, 1 meter per second per year for nearby sources, versus 0.4 to 0.2 meters per second per year for sources further away. Okay. I can now go to the conclusion side, but I do want to show a bit of modeling, because I have a minute or two left. We try to model this, of course, because this is only an observation. And I really like this picture because it looks quite convincing. On the left are the observations, and this is distance on the horizontal axis. We know the source receiver distances, and celerity on the vertical axis. Very simple. On the left is the model, and color-coded is the number of events, so 15,000 events in general. On the left are the observations, on the right is the model. And the model is ECMWF era 5, spheric specification, over that period of 20 years, 15, 20 years, and a simple ray tracer. Yeah, but you see, we can quite well reconstruct the observation with the models. Now let me go back, because we know from the models, and I can go forward, we did the same thing as a function of time. I don't have time to explain that now, but of course we try to reconstruct in the lower frame here the observations as a function of time too. And we're not fully there yet, but we are getting the positive trends we have observed. We are getting them from the models too. So what I think we are seeing is the following. The modeling results are consistent with a tropospheric warming of 0.5 Kelvin per decade. That's in the model, in the models too, of course. Huh? We saw that the effect was much larger at nearby sources than sources far away. Up to 200 kilometers distance, the numbers were larger than 200 to 900 kilometers distance. I think that's because we see a simultaneous effect, because while the troposphere is warming, the stratosphere is cooling. So the troposphere, the first 10 kilometers, is warming at 0.5 Kelvin per decade, but because of the balance, the stratosphere is cooling at approximately the same rate. But when I go to larger source receiver distances, much more of the path is in the stratosphere. So the fastness that we get, the medium becomes faster in the troposphere because of the higher temperatures. This effect is somewhat reduced in the observations because of the cooling of the stratosphere, which again slows down the energy. And that's really exciting. Huh? So I think we are capable of simultaneously observing a warming and a cooling atmosphere. But you have to be careful, and that's why there is a note. And I'm running out of time.
3 minutes.
3 minutes.
3 minutes. Oh. There is a note. We have to be a bit careful here, because a warming troposphere means an expanding troposphere. So the troposphere is becoming thicker at about 50 meters per decade. Simultaneously, of course, the stratosphere, the higher thing, is contracting at about 100 meters per decade. For the infrasound specialist, when things are warming and cooling, launch angles and refraction altitudes start to change. Well, also the thickness of this layer is changing. Yeah? Well, 100 meters or 50 meters, well, we're looking at 1 Hz signals, so wavelengths of 330 meters. Not immediately something to worry about, but if you go to time spans of 20, 30 years, we are getting into the range of the wavelengths for the things we are sensitive for. Huh? So for sure, please repeat this analysis, but be careful. We have to take more into account than just a medium becoming slower or faster due to temperature change. Also, the thickness and refraction altitudes are changing. To conclude, the IMS has been operational for tens of years. And this is the good news, will stay operational for decades to come. Nobody wants to lose the IMS. Such long seismoacoustic time series are very valuable, of course, for treaty verification, but also for climate study, and I think can serve as an independent proxy. Thank you.
So, one short question. We have time for, of course. Roger. Do we have a microphone?
Can you hear me?
I can hear you,
yeah.
loud and clear.
Do you have any intention to include experiment phases to further that, hold up high, warm down low?
Yeah, I think I don't get them from the data. The celerity range doesn't indicate much thermospheric. So it doesn't go down to the 0.2 something that we are used. On the other hand, at small ranges, you should always watch out with these standard values. So I think it's dominantly stratospheric. Actually, what I didn't show, if you want to model this stuff, you need to assume Sergei's and Igor's partial reflections. Otherwise, you get nothing or hardly anything at the stations. So the data set is dominated by partial reflections from both the troposphere and the stratosphere. But there might well be low mesospheric, thermospheric stuff in there too. Yeah.
There might be other data sets, not just this.
Yeah.
Okay, thank you. Thank you, Läslo.
Thank you.
We go from waves in the atmosphere to gases in the atmosphere with the next speaker, Ms. Carolyn Seifert from Pacific Northwest National Laboratory, who will introduce us to a design of a radionuclide.
Thank you. And now for something completely different. First of all, let me start with what I'm going to present today is the work of a large number of people. I've tried to capture them here on this slide. There's a number of institutions in the US that contributed to this, including several DOE laboratories, the University of Texas, and NOAA. So I'm going to talk about the atmospheric radiotracer experiment that we designed and conducted in the past year. Okay, let me start with a little bit of context. If you were present for the NNSA Deputy Administrator's talk on Tuesday, she mentioned that the US is conducting research in low-yield nuclear monitoring. So the work I'm going to present today is part of that program. We have, as a piece of the LYNM program, a large-scale experimental testbed at the Nevada National Security Site that we have instrumented with over 1,000 sensors, both below ground and at the surface. And the purpose for this experiment location is to execute multiple experiments that capture the multi-physics signatures associated with detecting and characterizing nuclear testing. So as a part of this, there are chemical explosions, an electromagnetic source, as well as atmospheric tracer experiments. What I'm going to talk about today is actually one of our atmospheric radiotracer experiments that we designed and executed in this program. I'll also note for our infrasound friends, this is one slide, my only slide that says the word infrasound on it. Okay, so when we think about low yield, we think about going to more local distances as opposed to regional distances to detect signatures. So we want to understand from a radionuclide perspective is how the topography may impact the near field atmospheric transport and how we might optimize local radionuclide detection networks. These are really critical questions. We also have a question about how we, at what scale do the, say, local and regional atmospheric transport models converge? We're going to try to answer the first two questions and part of the second question in this experiment. We know that complex terrain can complicate the transport of radionuclides, and we want to use this experiment to help validate and inform our models. So what did we do? We designed a 5-kilometer scale radiotracer experiment in which we conducted 4 releases of xenon-127. I'll talk about why we picked that isotope in a relatively complicated terrain. We deployed real-time sensors up to 5 kilometers downwind, and these included real-time xenon sensors made of sodium iodide logs, some MET stations to measure at high spatial resolution our atmospheric wind conditions, and as well as scanning LiDARs for particulate detection in the air, optical video cameras, et cetera. So a number of real-time sensors, as well as collected whole air samples for later laboratory analysis in order to validate some of our real-time data. So I'm going to talk about each of these components of the experiment in turn, and I will provide some initial look. I'll say we're just getting started on data analysis, so I'll provide an initial look at the data that we have. So let me start with the tracer release system. We are interested, of course, in radioxenon. And we selected xenon-127 as an ideal isotope for this experiment because of its, I'll say, relatively long but not too long half-life. This gives us time to produce it, ship it, work with it, send samples back to a laboratory without significant decay. But not so long that we have too low of activity and have to count for long periods of time. So xenon-127 was our selected isotope, and we produced it by irradiating stable xenon-126 in the research reactor at the University of Texas. We then built a tracer release system. I've got a picture of it in the upper right corner of the slide. In fact, this was 2 systems side by side in a testing event at PNNL. And what you see here is something that looks sort of like an aluminum box on stilts that houses all of the pump and manifold infrastructure needed to pull the xenon gas out of a canister and push it out into the air. You also see here there are these aluminum buckets that contained spoke candles that were remotely ignited to produce a significant particulate source at the same time as the xenon. From the source canister, we did collect aliquots of source gas so we could validate our actual release activities for radioactivity for each of the releases that we conducted. And then we synchronized in time the release of the xenon and the ignition of the smoke candles so that both of those would occur at the same time and continue for roughly 5 minutes. I'm showing a plot in the lower right from one of our releases. We monitor in this tracer release system both the pressure in the system, which is dropping as a function of time, that's the blue curve, as well as the flow rate of the xenon gas through the system, which we tried to maintain as constant as possible across the 5 minutes that we were releasing. And then you'll see on the far right of this graph, actually there's a stage after the release is complete where we do a pump and flush of the entire system. It sort of pushes the last little bit of xenon out of the system. So that's our source. Let me talk about some of our real-time sensors. We designed a network of sodium iodide-based radioxenon sensors. These were 2-liter detectors. In English units, that's 2 by 4 by 16 inches. We can convert to centimeters. And we packaged them for field use. That is to say, we gave them thermal enclosures and operated them on batteries and solar cells, connected them to a cellular network where we transmitted data in real time to a cloud-based analysis platform for us to monitor and control those systems throughout the experiment. We did a number of simulations to estimate the sensitivity of these detectors, assuming plumes of xenon-127. We estimated the detection threshold to be something less than about 10 becquerels per cubic meter. And if you saw Sean Stava's talk this morning, or his poster this morning, he talked more about the sensor design here. I'll point out that we have also through atmospheric transport models, we've estimated source dilution factors of something like 10 to the minus 9 to 10 to the minus 8 out at 5 kilometers. And if you remember from the last slide, which I think I forgot to mention, we released about half a gigabecquerel in each release. So what we're expecting is having concentrations of xenon-127 at the edge of our test bed at that's 5 kilometers that are just barely or maybe even just below our detection threshold. You see a picture here of these xenon sensors. They're oriented vertically on a tripod and some examples of data as we saw in the experiment. So let me show you where these are. As I mentioned, we're at the Nevada National Security Site. Can I do this? Let's find out. I cannot. Okay. So we're up near Aqueduct Mesa. That's basically the base of the mesa is where we did our releases from. And we had 4 arcs that we put these sensors out in to cover this area basically from a few hundred meters to 5 kilometers. And then at the same position, which I'll talk about a little bit later, at 5 of these positions, we co-located whole air samplers. From the base of the mesa, we had 2 positions that we actually released xenon from. We called them apron 1 and 4. They're labeled in the graph on the right. Because we have different wind patterns. Actually, they're not that far apart, but we have different wind patterns based on the local topology, and we wanted to understand the difference in what we may see from this network of sensors in these locations. We also had a dense network of meteorological sensors, including 11-meter MET towers that include pressure, temperature, humidity, wind speed, etc. We launched a radio sonde with each morning release that obtained a vertical profile of atmospheric conditions. We brought scanning LiDARs to measure the particulates from the smoke, and an energy flux tower for more detailed MET measurements. And although it's not MET, I'll add that we have video footage from a number of locations of the plume. One of the nice things about using both the smoke and the xenon is that we can watch where the plume goes in real time, and we have some video evidence of where that appears to be, and comparing the measurements from the scanning LiDARs to our radio xenon measurements is one of the goals of the data analysis that continues. So in the map on the right, I show we basically installed a MET tower along this road, along this 5-kilometer road, to get wind conditions in this valley. So as I mentioned, we successfully conducted this experiment and data analysis is underway. I'm going to show just a little bit of data, maybe whet your appetite, and hopefully at a future SnT we can present more detailed results. But for one of our 4 releases, I'm showing some data here. In the top right, we have summed count rates from several selected radio xenon sensors. We had a total of 22 in the field. I'm showing data from 6 of these. And these are summed count rates in the region of 20 to 220 keV in the energy spectrum. And you can see the red lines in each of these is the moment of the initiation of the xenon release. And you can see a peak in 5 out of the 6 of these. And I think maybe that 6th one you would say that one didn't actually see the xenon based on its count rate data, and it's not surprising based on its position. You can look at the graph on the map on the left. The blue arrow represents, I would say, a cartoon of where the measured wind conditions were. So we had wind approximately headed in the direction of south-southeast. And green circles represent xenon sensors where a positive detection of xenon was observed. red circles indicate no detection of xenon, and you'll find there's one yellow circle where further analysis is needed. I'm also showing some of the LiDAR data, including the backscatter and the radial velocity measurements, and you can see the evidence in the graph on the right of the smoke plume. That's actually the bright orange-yellow section. The dark section at the bottom of this graph is actually the topology, so that's actually ground, so you get sort of backscatter off that surface. And everything else above that is in the air, and you're getting a reflection signal off of the smoke particles. And I would say that our initial look at the LiDAR data in comparison to the radionuclide data is actually, looks pretty favorable. There's still more analysis needed.
2 minutes.
Thank you. We also collected whole air samples. We took 7 duplicate samples at each of 5 locations co-located with our xenon sensors. These samples were then measured both on-site as well as off-site at PNNL in a direct gamma measurement, as well as separating out the xenon and measuring it that way. And we find that with a direct measurement, we were able to, in this particular case of these 5 samples, we were able to detect xenon in 2 of the sample bottles. But then when we were actually separating out the xenon, we had lower detection thresholds, not surprisingly, and we're able to detect our xenon and quantify the concentrations that were collected at those samples. And as I mentioned, our data analysis does continue. This is our first look at the outcomes of this Radiotracer experiment. We spent a lot of effort developing a source release system, putting that sensors out, taking all of these data. It was a pretty large effort from a large number of people, a number of which are in this room. And so at this time, I'm happy to welcome any questions.
I think it's 1 question maximum.
Time for 1 question.
Thank you for a very great talk. I'm just going to have a short question. Did you have any vertical profiling with your sensors, or were they all on ground level? Did you try to collect xenon at altitude?
We did not collect xenon at altitude. It was one of the things that we considered in the experiment design, and in this case, we chose not to do it.
Thank you very much.
And the next speaker is Mr. Chen, who is remote detecting analysis of infrasonic signal of the massive 2015 Tianjin explosion event. Please. It's cold.
Cold?
Yeah, there it was. It's okay.
It's on speaker.
Yeah, but I couldn't say that. It's not for that.
Good afternoon, ladies and gentlemen. My talk is detecting and analysis of a massive chemical explosion in Tianjin of China. In my presentation, I will attach more importance on the signal detection and association algorithm. There are 4 sections in my talk. At first, I will give an introduction of our infrasound array and their improvement. Two original infrasonic arrays were set up in northwest China in 2009, and record a number of signals, including the famous Russia meteor explosion and famous chemical explosion in Tianjin of China in August 12, 2015. The event shown in the finger is a Russian meteor explosion on February 15, 2013. This signal is from our infrasonic array. And this is a comparison of signal from IM's signals. I attach great importance on the meteor explosion. Please observe two sets of signals. The above set of signals is from nuclear explosion from China, and the following section of signal is from Russian meteor explosion. I filter the signal with a frequency band of 0.02 to farads. If I lower the upper limit of the frequency band, I can get a signal that is identical to the nuclear explosion signals. So the key point is that the meteor explosion provide us a very important signal source for verifying our measurement and our signal processing. Okay, I will give an introduction of our design of infrasound array and improvement. Each element of our array have a denoise pattern like this. To make full use of space, we arrange the ion inlets in a spiral line.
Can you please use the microphone? Because you are speaking.
Okay. We arrange the ion inlets in spiral lines. In the future, we will arrange the ion inlets in spherical spirals, and the sphere is filled with soft steel wires. We hope we get a better performance of denoise, will reduce the size of the pipe largely. In the second section I will introduce our signal detection algorithm. In the field of infrasound processing research, we are all familiar with the STA-to-LTA and the PMCC algorithm. To overcome the defect of the low performance of STA-to-LTA detection algorithm and higher false alarm range of PMCC algorithm for low SNR signals, a novel slowness estimation detection algorithm is presented, that is SED. The slowness of the normal signal is distributed in a range. They are neither too low or too large nor too small. When the slowness estimation is distributed in the range, we accept it. When it outside the range, we reject it. To get more accurate estimation, we use two methods. One is from time domain and one is from key domain. This method is relevant. if the two estimation is consistent with each other and the slowness is distributed in the range, we will accept it and the detection is achieved. There's a problem. The SED algorithm is much time consuming. The amount of true signal is much less than that of noise. Most of the apparent noise can be eliminated first by simple detection algorithm. So we use a hybrid detection tactic. First use SnT2023, then PMCC, and in the end we use SED. The threshold for each detection algorithm is like this. The threshold for SnT2023 is 1.1. That means a very low SNR. And the threshold for PMCC is 1 sampling period. Here we'll give two applications. This is a mining exploring infrasound. The above signal is seismic, and the following is the infrasound. The SNR of the signal is too low to identify interactively, but our auto hybrid signal processing algorithm do the job very good. This is another application for a moving object. We obtain the azimuth variation with time. There's a much higher requirement for the detection algorithm. This is an application for the Russia meteor exploring. We obtain the azimuth variation with time. We can see the supersonic phenomena. In the third section of my talk, I will give an introduction of our signal association. A large number of false alarm events can be found usually in the association results if the association precision is based on the detection's arrival time and azimuth only. Compared with mature seismic signal processing, infrasound signal processing technology has been faced with great challenges for a long time. Infrasound propagation relies heavily on its own wave medium, and the propagation speed is slow, which makes the arrival error of infrasound extremely large. The amplitude of signal, quality of infrasonic signal are also severely affected by their fluctuating medium, the following atmosphere. The signal recorded by station in different positions in the downwind and the upwind direction have significantly difference, and the noise are also large, making it difficult to detect, identify, and locate. To overcome this problem, other signal features, including attitude, SNR, signal duration, dominator frequency features are incorporated into the association precision. By this way, improved results indicate above 80% false alarm regional events can be eliminated. Considering that the number of infrasound stations or arrays currently deployed on Earth is very small, and there are few available correlation signals, infrasound signal processing has become a low signal to noise ratio signal processing in spatial network, which put higher requirements on the detection recognition technology of infrasound. To improve the accuracy of association, we proposed a signal envelope correlation method.
2 minutes, please. 2 minutes.
Okay. The envelope extraction is based on wavelets packet decomposition. This is our procedure. We can see the envelope of the signal is a function of t of time t. Envelope we will process a transform of the envelope that is similar to the wavelets ft to fat, and then we calculate the cross correlation calculation of a signal envelope at a different distance distances. In the fourth section, I will give analysis of Infrasonic analysis of massive chemical explosion. A massive explosion in Tianjin occurred at a container port on August 12, 2015. The explosion produced a strong infrasound with extremely higher SNR registered by infrasonic stations thousands of kilometers away. Different from the ordinary exploring infrasound, Tianjin exploring infrasonic signals appear as 6 consecutive groups, each with clearly forced arrival. This reveals the complexity of the infrasound propagation path. The maximum amplitude of the infrasonic signal from our array is 11 pascals, and the array is nearly 2,500 kilometers away from the exploring source. The infrasonic signals of the event have a certain amplitude and SNR 3,500 kilometers away in the downwind direction and cannot be observed directly clearly several hundred kilometers away in the upwind direction. The yield of the explosion is estimated is about 400 to 600 tons of TNT. We also analyzed the seismic signals. Because it is a ground explosion, the seismic signal is not clearly from the nearby seismic stations. In the end of my talk, I draw a brief conclusion. The SED detection algorithm and the envelope correlation association algorithm work well in our auto signal processing for infrasound, but there is still a lot to say about signals arrive time, azimuth, and mountain pass phenomena because of flowing atmosphere. Thank you.
Thank you.